Hi there. I'm going to talk you through the last minute review, just sort of a brief summary of everything. If you check out this document on Moodle, there's this quiz through review, which is mostly about degradation and recycling options for polymers and plastics. We really started our transition from biodegradation options into the properties and really relating those two. So we're really starting at week 5. So as you recall, we talked about crystalline versus amorphous versus microcrystalline or semicrystalline. Those words are kind of interchangeable. So what this really means is whether or not all the chains are completely organized if it's crystalline. Amorphous means they're all random and messy. And microcrystalline is somewhere in between. So usually there's a fade. So we're usually in some point in between these two. It's rare that we have perfectly crystalline or perfectly amorphous. The glass transition temperature is really the point that moves us between. You can have something that is organized and more crystalline or glass-like, and then when you melt it, and it's not a complete melt, remember, it's still a solid, it becomes a little bit more loose. Some of the parts start wiggling around and they can move. So it's completely frozen and then a little bit of wiggle room, essentially. So you're moving between those two. And both of these matter when we talk about biodegradability. So if something's completely crystalline, it's hard to degrade because you can't really access it. Everything is nice and organized. When things are organized, they usually are packed nicely together. So you can't really access it. It's hard to get in there. If something has a high glass transition temperature, it also means things are stuck in place. You can't really move around. If it's beyond the glass transition temperature, then you can start moving things around and you could potentially bacteria or other degradants could get inside. We also talked about this in relationship to solubility and how well polymers will mix together. We saw lots of polymer blends in fabric, for example, that's mixing, which is different than a copolymer. Solubility really depends on the structure. Most polymers are not very soluble. If they are, it's usually things that are not just straight chain. So we saw, for example, and I'm going to go to our How Polymers Are Made and Polymer Textiles document. So we can look down here. The reason that you can partially dissolve PET, and we saw polystyrene with our own eyes dissolve in acetone in lab. It's because of this benzene ring. So this actually gives it a group that's kind of sticking off, and it will dissolve. Where the rest are just tightly packed in. So if you see polyethylene, for example, the next chain of polyethylene can easily pack right underneath of it. So they can get pretty close. You can make it very low density, so you could actually add branches and make it stick off and down to make things like saran wrap to prevent it from packing. So really how well they stick together. So I could make this polyethylene move this way and then stick another one and make it come down this way. And that would create a lower density version. It's the same material. It is just branched to prevent it from packing. Okay, so then we talked about cross-linking. Cross-linking is another way to get them to pack in tight and hold them tight together. Once something is cross-linked, it strengthens it significantly. You would significantly increase a glass transition temperature if it had one at all. Some things don't even have it because there's no freedom of movement at all. When we talked about cross-linking in nylon, for example, what we really discussed was the way, let me go to this one, sorry. the way that they organize. So in nylon, we specifically talked about the fact that there were these O's here, one down, one up, and then there's these nitrogens with hydrogens here. That NOH section right here, NHs really like to stick to O's. That's what a hydrogen bond typically entails. H and O's, if they see each other across different molecules, they will try to line up just like in water. So what happened was, the reason nylon is a bit tough and makes a good fabric that has good abrasion resistance is one of these will stick on top of another one, and they will line up so that this H is in line with this O. This H could be in line with that O if it points down. So that actually takes something that's very flexible and increases its TG and melting temperature a bit more. This is why nylon is not very heat stable, right? It's 50 degrees. Remember, water boils at 100. So at 50, it starts getting a lot more flexible. So ironing this and going to hot settings isn't always a great idea. It might completely lose its structure. Meanwhile, we can go down here to things like Kevlar. The reason Kevlar is so tough is hydrogen bonding. See how Kevlar is similar to nylon. It has O's and it has these NHs. But what's different is it has these benzene rings. Benzene rings are flat and they're rigid. You can't flex them around like a chain. So you have this more rigid polymer to begin with, less flexible. It will organize such that the hydrogen bonding, so this is one chain of Kevlar, the next polymer unit below sets itself up so that you have this NHO. This is not an actual bond. These are not permanently connected. A hydrogen bond, though, is like a really strong Velcro. So they're just really tightly held together. And because of their structure and shape, they line up. So the whole thing is this organized, cross-linked, really tough material. All right, we talked about solubility and how most of these are not soluble. The ones that we did see dissolve were, we saw polystyrene, which dissolved a little bit more in acetone. Well, it completely dissolved in acetone. And it's again because of that ring. This sticks out. So you have this polymer chain with this benzene sticking out. And this will actually help it dissolve in the acetone. So some of them are going to dissolve. We also talked about, cross-linking a lot. We talked about mixing in terms of, this is when you actually have a polymer blend, which a lot of fabrics have, because we're trying to get some of one property and some of the others. Mix them all together. They're not copolymerized. They're different chains. They're just mingled together, mixed together. Tacticity was all about the direction that something is pointing off. So we talked about this in terms of polypropylene. Polypropylene has, unlike polyethylene, the carbons are sticking up. So there's 1, 2, 3 in the unit, right? This is the unit, the 3, for the propyl. So when they stick up, they could all stick in one direction. They could be random. They could go A, B, up, down, have some kind of organization. That will really change how well they can pack together. So that term doesn't apply to simple polymers like this. There is no up, down. But it will apply to, you could think about it in terms of polystyrene. But usually we're talking about polypropylene. We also talked about polymer size and polydispersity index. Polymer size is basically how many N units there are. Polydispersity index is how many are close together in size. What is that range of units? Remember that synthetic plastics usually get bigger, more ends than natural polymers, which is also makes them, there's more bonds, they're harder to break down. We also spent a lot of time talking about condensation and addition. Condensation usually involves water and hydrolysis. And you can recognize that from waters coming off during the synthesis. If a water comes off, it can go back on. So we talked about a few different fabrics below. We also talked about addition. That usually involves a direct CC bond. This is true in things like polyethylene. And I'll direct you to the top of this page here where we saw this is an addition polymer. We have all carbons in here. Where a condensation, the H here and the OH there comes off, and we're left with O, C, and N. This is the same bond that occurs in peptides and our proteins, so it's a biologically common bond. It's pretty strong, but there are plenty of enzymes. Nature is used to breaking this down, so it's not as difficult of a problem. Remember that 1 and 6 are the polymers that are more susceptible to light. So we learned just yesterday that pool noodles, for example, usually are polyethylene. They might be expanded polyethylene, meaning they have more air stuck in them to make them fluffier. But if we put anything with a benzene ring, the reason is benzene itself is more susceptible to light. So things like polycarbonate are susceptible to light, and polystyrene turns yellow under the light. It turns brittle because the light can attack this benzene ring. Same is true for polyethylene, so PET. And it could be true for Kevlar, right? Anything that has these benzenes, the light will start to attack that. So it depends what you're doing with those. So if we're going to learn about styrofoam in the ocean, the exposure to salt and all that UV light, polystyrene is a 6, actually changes the story a little bit versus if you throw polystyrene into a garbage dump. Then we talked about all the fabrics. So we talked about how the higher the TG, the more likely you can iron it. We talked about how cross-linking will affect the properties. More cross-linking leads to tougher fabrics. The 3 main fabrics were polyester, nylon, and rayon. So this has ester bonds that are potentially biodegradable. Nylon has the amide bonds like proteins. Rayon is semi-synthetic because it starts out as wood or cotton. So when I asked you to look at your fabrics at home for a previous lab, it was really asking you to see this relationship. And many of you noticed that you couldn't iron certain things very easily if it has a low TG. So pointing out TGs again, remember that you can make a really low TG. So for example, polypropylene has a TG at negative 10 degrees. That's below the freezing point of water. So at room temperature, you've already gone above the TG. That's why polypropylene containers are flexible. They're not melted unless you get all the way up here. The reason that we liked polycarbonate so much early on was because its TG is 145. 145 is well above the boiling point of water, which is 100. So we liked this. We could use it for baby bottles. You could sterilize it, pour boiling water in it. That was great. Except for the fact that one of the monomers right here is BPA. So the safety concerns are really about unreacted BPA. So this video only allows 15 minutes, so I'm about to run out of time. The rest of it we're still discussing. So I just wanted to hit those last concepts. Polymer additives, remember the main ones.